Annenberg Media.
More than 300 years ago in Ireland, Archbishop Ussher calculated the age of Earth based on the book of Genesis. He determined that our planet was created 4,004 years before the birth of Christ, on the 26th of October, at 9 o'clock in the morning. Widely praised by scholars and theologians, Ussher's calculation was not seriously challenged in the Western world for almost a century. Today, scientific evidence indicates that Earth is much older than biblical text suggests. By counting growth rings, botanists have found trees as much as 8,000 years old. And with the development of radioactive age dating, geologists have concluded that our planet came into being not thousands, but billions of years ago.
Humorist Mark Twain once remarked, "Nothing hurries geology." He was referring, of course, to the almost imperceptible geologic change that one sees in a human lifetime. No aspect of this science is more difficult for most people to grasp than the concept of geologic time. Our lives are governed by events that are measured by clocks, in seconds or minutes or hours. At most, we may plan months or years in advance. But to understand the nature of Earth, we need to stretch our concept of time beyond our human experience and into a geologic frame of reference. Events in Earth history, such as the development of mountain ranges, the rifting apart of continents, and the creation of new ocean basins, have been repeated over and over. And each of these geologic events takes place over many millions of years. The estimated age of Earth itself is over 4.6 billion years, an incomprehensibly vast period of time. One way to illustrate the immense panorama of geologic time is to draw an analogy using a time period that we can easily relate to. So let's condense the entire age of the Earth into one calendar year. On this scale, the Earth and its neighboring planets were formed on January 1st. By sometime in early March, the planet had cooled sufficiently to allow water to stand in pools on its surface. The very earliest forms of life appeared by late March, and oxygen gas became an important part of Earth's atmosphere beginning sometime in late July. Multicellular organisms appeared by October 25th, but it was not until late November that plants and animals were abundant on land. On about December 15th, the dinosaurs appeared, but disappeared in a sudden mass extinction on December 25th. The first humans appeared at about 11:20 p.m. on December 31st. And the Industrial Revolution began less than a second and a half before midnight. The first person to realize the immensity of geologic time and begin to investigate it in a systematic way was an 18th century Scotsman named James Hutton. His observations and ideas about the origin of rocks began as a pastime that he shared with other wealthy intellectuals of Edinburgh society. But Hutton's interpretations and conclusions ignited a major controversy throughout Europe and survive today as the foundation for modern geologic thought.
James Hutton was born in Edinburgh, Scotland in 1726. Like most intellectuals of his time, he explored many disciplines, from law and medicine to chemistry and agriculture. And it was this last pursuit that was to lead him into the field of geology.
he had been left a little piece of land, and he decided to become a farmer. So he went to Norfolk, England, and lived with a farmer for a couple of years to learn how to farm, and farmed for 15 years. But while he was farming, and all of his neighbors believed that he was a perfectly good farmer, he was spending a great deal of his time looking and becoming more and more fascinated with the land, what was under the soil that he was tilling.
An important question intrigued Hutton. He saw that land is worn down in many places by the destructive forces of erosion. How, then, was it possible any land was left to support life? He believed there must be an undiscovered force building up the land, which counteracts the processes wearing it away. He began searching for evidence of this force, and soon found it. Hutton observed that streams washed sand and gravel into the sea, where this sediment accumulated in offshore deposits. He found similar material in the form of ancient sedimentary strata, tilted and raised above sea level. Surely, Hutton thought, these layers must also have formed underwater, then risen to become new land. Hutton also described a type of geologic structure called an unconformity, in which one group of layers is truncated by another. He reasoned that unconformities form when strata are tilted, uplifted, and eroded, then buried by younger successions of strata. The presence of unconformities in many outcrops indicated to Hutton that the land was molded by repeated cycles of uplift and erosion. This idea was in profound conflict with the biblical view, which held that the land had been created all at once. Of Earth history, James Hutton wrote, "We find no vestige of a beginning, no prospect of an end." Hutton was the first scientist to show that the world must be far older than most people believed.
One of the most astonishing things to him, and one of the most important elements of his work, was to try to establish that, in fact, geologic time was a very long period rather than the biblical creation time by Archbishop Usher sometime later at 4004 BC. But Hutton was convinced that geologic time was very extensive.
Hutton reasoned that if it takes about a year for a river to deposit a millimeter-thick layer of sediment on the sea floor, then it must take at least 1 million years to lay down the 1,000-meter-thick sequences of sedimentary rock that he had observed in some parts of Scotland. Many church authorities were stung by Hutton's research, and not only because he claimed the world is much older than the Bible implied. Hutton also showed that supernatural events like the biblical flood aren't needed to explain why the world's surface looks the way it does. Ordinary processes, seen every day, could produce the same landscape, given enough time. Hutton concluded that these processes have operated in the same manner throughout Earth's history. This idea became known as the theory of uniformity, or later as uniformitarianism. The principle of uniformity underlies modern geology. For example, the presence of vast amounts of layered rock in the Grand Canyon can be explained as the result of ordinary sedimentation operating over millions of years. Such vast spans of history have been distinguished from more modest everyday experience by a special designation, geologic time.
Although arguments about the age of the Earth raged among the intellectual community throughout the 19th century, most scientists have accepted the premise that the Earth must be millions of years old instead of just a few thousand. And although they were not yet able to measure the age of rocks, geologists realized they could determine the sequence of events in Earth history by combining careful observation with some simple logic. They first reasoned that any layered sequence of rocks is formed with the oldest layer at the bottom and successively younger layers on top, This principle, called superposition, allows us to place rock units in a historic sequence according to their relative age. They also observed that layered rocks, such as lava flows, volcanic ash layers, and sedimentary rocks, are deposited under the influence of gravity. For this reason, the rock layers themselves are horizontal. According to this principle, known as original horizontality, rock layers that are folded or tilted must have been tectonically deformed, and this had to have happened after they were deposited. And finally, any geologic feature that cuts across or truncates a group of rocks has to be younger than the rocks that are cut. So features such as faults, intrusions of molten rock, and erosional surfaces can also be placed in a relative age sequence using this principle, called cross-cutting relationships. Although these geologic principles are based on nothing more than common sense, they are absolutely fundamental to the interpretation of Earth history.
According to the principle of original horizontality, beds of sediment form as horizontal layers as the sediment settles under the force of gravity. The principle of superposition maintains that the oldest layers of undeformed sedimentary strata are on the bottom and the youngest on top. Finally, the principle of cross-cutting relationships states that a rock is younger than any rocks it cuts across, as in the case of veins of igneous rock cutting across strata, or of unconformities, such as Hutton studied.
The principles of relative age dating are simple and yet so powerful that they were used by early geologists in the 18th and 19th centuries to construct a complete historic sequence of all of the rocks in Europe. And because rock formations in a sequence like this often extend over a large area, they can be used to correlate rocks from one sequence with historically equivalent strata in other regions. This is easy to see in a place like the Grand Canyon. This formation, the Kaibab limestone, can clearly be recognized in the sequence of sedimentary rocks on the opposite side of the canyon. And because it's the same formation, it marks the same period of geologic time in both places. Some rock layers persist laterally for thousands of kilometers and can be recognized in different places by their thickness, mineral composition, and other characteristics. For example, volcanic ash from the 1980 eruption of Mount St. Helens has been identified in sedimentary sequences as far away as Minnesota and Arizona. Rock formations can be valuable time markers, but correlation is difficult over great distances because physical continuity and rock characteristics can be ambiguous. Fossils, like these shells of marine organisms, can be extremely valuable time markers. Each fossil species has its own lifespan, and rocks that contain fossils with overlapping lifespans are actual time markers that can be recognized wherever they're found. The use of fossils in making geologic time correlations was first discovered in the 15th century, and by the beginning of this century, geologists had used correlation to extend the historic rock sequence from Europe to every continent on Earth.
The word fossil refers to any evidence of a prehistoric plant or animal that has been preserved in rock. Sometimes, part of the organism itself remains intact. In some instances, recrystallized or petrified, like the trees in a petrified forest. In other cases, the organism may have been completely dissolved, leaving only a hollow mold of its own image. Throughout geologic time, fossil species succeed each other in a distinct, recognizable order. In general, progressively older fossils are increasingly different from life forms today. This observation came to be known as the principle of faunal succession, one of the strongest lines of evidence supporting Darwin's theory of evolution. The 19th and early 20th centuries were the heyday of the amateur paleontologist, or student of old life. These fossil hunters, combing the cliff faces and quarries of the globe, identified thousands of fossil species and painstakingly established their relative ages from the positions of the rock layers in which the fossils were entombed. Regardless of where on Earth fossils are found, they always occur in the same sequence relative to one another. Some of the lower rock strata in the Grand Canyon contain fossils of the same general groupings as those in certain very ancient rock layers found in Wales. Since the ancient name for Wales is Cambria, these rocks were called Cambrian rocks, and the geologic period in which they were formed, the Cambrian period. 19th century geologists used the names of places and ancient peoples to label other times in geologic history as well. For example, the Ordovician period, the Silurian period, and the Devonian period after Devon in southern England. Characteristic rocks and relative positions of strata were also used to designate new time units. And gradually, the geologic time scale was constructed.
The standard geologic timescale is based really on the law of superposition. The oldest rocks are on the bottom and the youngest rocks on the top. Looking at rocks in various parts of Western Europe, it was recognized that certain formations could be correlated from one region to another, and the older rocks were very distinctive with a distinct group of fossils in them. The younger rocks overlay the older ones. They had different colors, different characteristics, different fossils. By arranging them sequentially, which ones were the oldest and which ones were the youngest, they were able to establish a chronology just on the basis of superposition. Each of the rock units took a name from the organisms that were in it or the region where it was first studied, giving us the modern geologic timescale.
The relative age relationships that we see in rocks allow us to recognize geologic events in a historic sequence through time. But knowing only the order of events is a bit unsatisfying. Without the ability to measure the absolute age of these rocks, it's impossible to fully understand Earth history. And without a calibration of geologic time, we can't study the rates of geologic change that are used to make forecasts about future events. Scientific discovery is often born of chance events coupled with keen perception. In the late 19th century, Madame Marie Curie discovered that when certain types of rocks were stored in the same drawer overnight with undeveloped photographic film, the film was exposed. This chance event led to the discovery of radioactivity. In this process, certain types of atoms spontaneously disintegrate or decay. The decay is random, but it proceeds at a constant rate through time for each particular type of atom, or isotope. Because many different types of rocks contain radioactive isotopes, Ernest Rutherford reasoned in 1905 that the uniform rate of radioactive decay could be used to measure geologic time. From this realization came the eventual development of techniques to measure the absolute age of geologic materials. Now, for example, not only do we know that the dinosaurs disappeared in a global mass extinction, we know it happened 64 million years ago.
Each element can be separated into isotopes, groups of atoms with similar atomic structure, though slightly different mass. Some isotopes are radioactive and therefore unstable. This instability causes the atoms to radiate energy, much of it in the form of electrically charged particles. The radiation gradually causes the element to disintegrate or decay, transforming the original radioactive isotope, or parent, into a stable isotope, known as a daughter product. It is this process of decay that we call radioactivity. Grains of sand trickling through the narrow opening of an hourglass are somewhat analogous to isotopes decaying in a radioactive element. The sand in the upper half of the hourglass represents a supply of parent isotope. The sand in the lower half is its daughter product. The proportion of parent to daughter depends upon how much time has elapsed. This can be determined simply by measuring the ratio of parent to daughter sand. This is how radioactive dating works. The most familiar example is radiocarbon dating. The carbon in air and water is made up of 3 different isotopes. One of these, carbon-14, is radioactive. As part of the atmosphere, carbon-14 is absorbed by living plants and animals. In this way, the carbon in all living organisms contains the same proportion of carbon-14 to non-radioactive carbon. When the organism dies, it stops taking in any new carbon, and the amount of carbon-14 inside it gradually decreases as it decays. It is this shrinking proportion of carbon-14 that tells us how long ago the organism died. The rate of decay of any radioisotope is measured in terms of its half-life, how long it takes for half of its atoms to decay. The half-life of carbon-14 is 5,730 years. Carbon-14 is most commonly preserved in the form of charred wood that is buried by sediment, lava, or volcanic ash. If a sample contains only half the level of carbon-14 found in living organisms, geologists conclude that it must be 5,730 years old. If the ratio of carbon-14 is only a quarter that of a living organism, another half-life has elapsed, and it must be 11,460 years old, and so on. This method is only reliable for dating things back about 50,000 years. Beyond that, the amount of radiocarbon remaining is too small to permit accurate measurement. To date rocks that are millions or even billions of years old, geologists work with radioisotopes that take much longer to decay, such as uranium-235. This element makes an excellent geologic clock because it takes 713 million years for half of it to decay into lead-207. By measuring the relative amounts of these 2 isotopes in a rock, it's possible to figure out the rock's age, even if it is several billion years old.
The first step in determining the age of the rock is finding the proper rock in the field and determining its mineralogy. Once we've determined what it is we want to date, then we sample it in the field, bring it back into the laboratory, separate out the minerals that we want to date that tell us the age of the rock. Once we have a clean mineral separate, then we take it into the laboratory and we separate out chemically the elements that are within the rock that have the isotopic system that we're interested in. And then, once we have the elements separated, we bring the elements into the mass spectrometer, and with the mass spectrometer, we analyze the isotopes of the elements that we're interested in. And it's the isotopic ratios between the parent and the daughter isotopes and between the various daughter isotopes that give us the age of the rock.
The mass spectrometer accelerates the ions, or charged atoms, of an element so that they form a beam, which is then spread out into a succession of points, a mass spectrum. From the position and intensity of the points, the mass and relative abundance of individual isotopes can be determined.
Once the element that we're going to measure is loaded in the mass spectrometer, it's ionized at a temperature between 1,000 and 2,000 degrees centigrade, depending on what element it is. The ions are then accelerated by 8 to 10,000 volt drop down the tube, which is a high vacuum tube. And as they're being accelerated, they're focused into a very fine beam. Once they enter the tube as a fine beam, they move through a magnetic field. The magnetic field puts a drag on the ion beam, which causes the heavy isotopes to bend along the outer part of the tube and the lighter ones into the inner part of the tube. By the time the beam comes out of the magnetic part of the tube, it's broken into its various isotopes, and at the far end of the tube, we count the ions of each isotope, which ultimately gives us our isotopic ratio.
The complete process of collecting rock samples, preparing them for analysis, and doing the mass spectrometry requires a great deal of time and skill.
Then you finally get to the point where you put the final bit of data into your computer and calculate your age. And at that point, it all comes to somewhat of a crescendo, and you get very excited, and there it is, finally, you have your results. And sometimes you're totally surprised, sometimes you're disappointed, and sometimes you're elated with your results. And then the final, of course, aspect of it is really applying the age data to your actual geological relations.
Minerals which contain radioactive isotopes act like tiny clocks inside of rocks, clocks which are reset when a rock is formed or metamorphosed. Before geologists learned to measure the absolute ages of rocks using radioactive isotopes, they could only establish relative ages using the common sense logic of superposition, original horizontality, and cross-cutting relationships. They knew that one rock formed before another, but never how old the rocks actually were. The reliability and accuracy of radiometric age dating is truly impressive. The results of over half a century of radiometric age dating studies are entirely consistent with the relative age relationships developed by early geologists. So the science of geology has given us two ways to understand Earth history. First, we determine the relative age of rock formations and geologic structures, and then use these ages to construct a historic sequence of events through time. Then, by applying radiometric age dating techniques, we determine the absolute timing of these events and measure the rates of geologic change as well. So not only does our study of geologic time allow us to understand Earth's past, it gives us a historic framework and the tools for predicting the planet's future.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.